Good morning, students. I'm Dr. Betty, continuing with the nuclear chemistry, lesson 2. In lesson 1, we looked at the nucleus, and we said an atom contains positively charged core at its center called the nucleus. We further went to look at the definition of the nucleus, where we said that a nucleus is the central part of the atom, which is positively charged, dense, and rigged. And we said that the positive charge is due to the presence of the protons. We looked at the properties of the nucleus, which included the size, density, and we said that the size of the nucleus is smaller than that of the size of the atom. Then we said that the density of the nucleus is the same for all the nuclei. When we looked at the composition, we said that the nucleus is composed of protons and neutrons. And the mass of the nucleus is equal to the sum of the protons and the neutrons. Another property, we said that a radioactive nucleus can emit alpha, beta, gamma, and other particles. Today, we are going to look at the forces which operate inside the nucleus of an atom. Electrostatic force. This is the force acting between the two charged particles. This force may be repulsive electrostatic force or attractive electrostatic force. Therefore, the forces acting inside the nucleus are mainly two: the repulsive electrostatic force and the attractive electrostatic force. The repulsive electrostatic force. Since the nucleus of an atom contains protons, the electrostatic force acting between them is repulsive electrostatic force. This force usually causes repulsion between the various protons present in the nucleus and hence makes the nucleus unstable. Another force is the nuclear force or attractive force. This is the force which, without considering the nature of the charge on the proton and the neutrons, causes attraction between proton and protons or protons and neutrons. This force becomes large in magnitude when the various protons and neutrons or nucleons are very close to each other. Remember, we said the nucleons is the same as protons and neutrons. Due to its attractive nature, it is a stronger force and holds together the nucleons in the nucleus and thus makes the nucleons stable. Reasons why small nuclei are stable while big nuclei are unstable. Small size of the nucleus of an atom of a small element, the various protons and neutrons in it are very close to each other. And hence, the force of attraction between the nuclear particles is large. The nuclear force of attraction has been found out that is much greater in magnitude than electrostatic force of repulsion. Therefore, smaller nuclei attain stability. For big atom, the nucleus is also big in distance between various nuclear particles. The nuclear force of attraction and the electrostatic force of repulsion between these particles therefore decreases. It has also been found out that the magnitude of electrostatic force of repulsion becomes slightly greater than the nuclear force of attraction. And as a result, the electrostatic force of repulsion dominates. The nucleus becomes unstable and hence disintegrates by emitting certain particles. An example is uranium-235. Uranium-235 is an example of big nucleus in which the electrostatic force of repulsion is greater than the nuclear force of attraction. And hence, uranium-235 nucleus is very unstable, due to which it can easily be broken into smaller nuclei. The fusion of uranium-235 nucleus can be done by means of slow-moving neutrons. An example of the equation is here: uranium-235 plus the slow-moving neutrons, and a fusion or breaking into one barium-139 and the krypton-94 plus 3 neutrons, and some amount of energy is released. Nuclear stability. Some isotopes are stable while others are unstable, that is, radioactive. Stable nuclides are not able to undergo spontaneous disintegration, while the radioactive nuclei undergo spontaneous disintegration. The stability of the nucleus of an atom is called nuclear stability. Now let us look at the factors that affect the nuclear stability. There are mainly 5 factors. The first one is even and odd number of protons and neutrons. The next is a neutron to proton ratio. The third one is packing fraction, abbreviated as F. The fourth is binding energy per nucleon. And the last one is the nuclear shell model, or you can call it the Magic number. Let us first look at the packing fraction. It has been found out that the isotopic mass as determined by the spectrograph is not the same as the mass number of the isotope. When the difference of the isotopic mass minus the mass number times 10 to the power 4 is divided by the mass number, we get what is known as the packing fraction of the isotope. Thus, packing fraction is equal to isotopic mass minus the mass number times 10 to the power 4 over the mass number, or M minus A times 10 to the power 4 over A, where A is the mass number. Therefore, we can define the packing fraction as the difference between the mass of an isotope and its mass number divided by the mass number. Then the answer obtained should be multiplied by 10 to the power 4. Therefore, an example: one chlorine isotope has a mass number of 32.986 and the mass number of 33. Its packing fraction is therefore, so we said in the equation above, or in the formula, that the isotopic mass minus the mass number times 10 to the power 4 over the mass number. So if we apply that here, we are going to get the isotopic mass, which is 32.986, minus the mass number, which is 33, divided by the mass number, we shall get negative 0.00042. Then we said that the packing fraction are often multiplied by 10 to the power 4, so this answer will be negative 4.2. Let us look at the relationship between the stability of the nucleus and its packing fractional value. If the value of the packing fraction of the nuclide is negative quantity, then the nuclide should be stable. And usually the negative value is obtained when the mass is less than the atomic mass or the mass number. If the nuclide has low positive value of packing fraction, then the nuclide should be stable. The nuclei having very high positive value of packing fraction are unstable, and hence such a nuclide undergoes spontaneous disintegration. Also, the positive value is obtained when the mass number is greater than the mass number. Activity 5. Calculate the packing fraction of argon isotope. Mass of the isotope of argon is equal to 39.962384 mu. What does the value of the packing fraction imply? The above question can be answered as follows. We know that the packing fraction of argon is given by mass of argon minus the mass number of argon times 10 to the power 4 over the mass number. So this is the same as 39.96238 minus the mass number, which is 40, times 10 to the power 4 over 40, and the answer is equal to negative 9.404. Remember, in the previous slides, we said when the packing fraction is negative, it means that isotope is stable. So next time, we are going to look at mass defect.